Welcome everybody to our presentation. This is Business Math. We are discussing the derivative of a logarithmic function. This is Magda Talib Al-Hinai from Sultan Qaboos University, and I welcome you all. In this presentation, we're trying to find the derivative of ln x. We start from the definition of the derivative as a limit. So we write the derivative of ln x with respect to x is equal to limit as h goes to 0 ln of x plus h minus ln x over h. Next, we use the property of the logarithmic functions where logarithm a minus logarithm b is equal to logarithm of a divided by b. So in the coming step, we will split this into two fractions with the same denominator, x over x plus h over x. X over x we put 1, so here we have limit as h goes to 0 ln of 1 plus h over x divided by h. Now we multiply by x and divide by x. And then we take this red x, the 1 over x outside, and we keep here x over h. So we are rewriting this whole thing again in another way. Now we will use this property. C times ln A is equal to ln A power C. This is our C, and here is A. So now we have 1 over x outside, limit as h goes to 0, ln, and we took the x over h and here we put it in the exponent. Now for x greater than 0, we can say instead of h, we can put h over x. Okay, next we use the property of the limit where we can calculate the limit of the bracket inside because we have a logarithmic function which is continuous. So here we make the limit enter inside the ln. So now we are taking the limit of the bracket here. Can we put instead of x over h any other variable like k for instance? See, we replaced every x over h with a k, and here we put in the exponent 1 over k. Of course, we know that this limit is equal to e. Now we have 1 over x, ln instead of ln of limit. No, the limit is reduced to e, the natural exponent. So here we have ln and e, a function and its inverse. So this is equal to 1. So the whole thing reduces to 1. In other words, we were able to say to calculate the derivative of the logarithmic function ln x, where x is greater than 0. And here we go. We move on with the derivative of a logarithmic function. Here we have the derivative of ln of absolute value of a function u of x. Here we apply the chain rule. We have 1 over inside times derivative of inside. And of course, inside is not equal to 0. So this is another way of writing it to make it easier for you to remember it. 1 over inside times derivative of inside, and inside is not equal to 0. Let's take an example. Differentiate y equals to ln x squared plus 1. Here we did not put the absolute value because we are sure that x squared plus 1 is greater than 0. So we say y prime equals 1 over inside times the derivative of inside, which is 2x. Let's see another example. Differentiate. Y equals x squared times ln 3x plus 1. Here we have the product of two functions, u and v. We take u to be equal to x squared and v to be equal ln to ln of 3x plus 1 as written here. We differentiate the u, we differentiate the v so that we apply the product rule for the differentiation of u, v. So u prime is 2x, v prime is 1 over inside times derivative of inside, which is 3. Next, we apply the product rule. So here we have x squared times the derivative of ln 3x plus 1. So it is 3x squared over 3x plus 1, where we use the v prime, which we got here. And then the second term, we keep the ln of 3x plus 1 as it is, and we differentiate the x squared to be 2x. And that's it, and we move on. In the present slide, we will discuss two important problems. First, we want to differentiate y equals ln of 5x squared plus 4 all cubed. Here, we will rewrite this y again using the property ln a power c is equal to c ln a, which is an important property of logarithmic functions. After having writing y equals 3 into ln of 5x squared plus 4, we will start to differentiate. So y prime is equal to 1 over inside times derivative of inside, which is 10x, or this is equal to 30x over 5x squared plus 4. Next, we move to another example. Differentiate y equals ln of 5x squared plus 4, the same function, but the 3 is not on the 5x squared plus 4. The exponent is not on this bracket only so that we can apply this property. No, the exponent is on the logarithmic function as a whole. So this means that y is equal to ln 5x squared plus 4 multiplied by itself 3 times. In this case, in order to solve such a problem, we imagine that we are differentiating a function power n and we apply the chain rule. So y prime is equal to 3, and then we have ln of 5x squared plus 4 power 2, we reduce the exponent by 1, times the derivative of what's inside the bracket, which is a logarithmic function. And how do we differentiate a logarithmic function? We all know that we put 1 over inside, which is 5x squared plus 4, times derivative of inside, which is 10x. We can rewrite this again as y prime is equal to 30x over 5x squared plus 4 multiplied by ln of 5x squared plus 4 all squared. We move on. In the previous examples, we were having the case when we had y equals ln of anything, of inside. Now we want to see how can we differentiate y equals log base b of u. So how can we deal with this? We do the change of base. Okay, so we rewrite log u to the base b. Of course, we have u greater than 0. We write it as ln u over ln b. This way we change the base to ln, and now we can differentiate, and we all see that ln b is a constant. So y prime equals 1 over b, which is the constant, multiplied by the derivative of ln u. What's the derivative of ln u? It's here. It is 1 over inside 1 over u multiplied by derivative of inside, derivative of u with respect to x. And also we have here to put that u is greater than 0. Okay, I write it in the way y equals log base b of inside. It will be 1 over ln b, because we changed the base, multiplied by 1 over inside, multiplied by derivative of inside. All this is giving us the derivative of y. Now we move to an example. Differentiate y equals log base 3 of x squared plus 5x. Here we are using this way of differentiation for the logarithmic function where we have the base b equals to 3. So here we have y prime equals 1 over ln b, 1 over ln 3 multiplied by 1 over inside 1 over x squared plus 5x times derivative of inside 2x plus 5, because inside is x squared when you plus 5. When you differentiate this, you get 2x plus 5. So we rewrite it in the following form, and that's the solution for this example. Next, we move further to take word problems. In this slide, we are going to discuss two word problems, the first in business and the second one will be in biology. In this problem, we are asked to find the marginal revenue function where we are given the demand function. So here is the demand function in front of us. P is equal to 25 over ln of Q plus 2. We all know that the revenue function is equal to P times Q, price times quantity. Here is P, so we multiply it by Q. We get 25Q over ln of Q plus 2. Now, in order to differentiate this, we are going to use the quotient rule. Here we have the U is equal to 25Q and the denominator V is equal to ln of Q plus 2. Now we differentiate the u to get u prime, we get u prime equals 25, and we differentiate the v to get the v prime, we get v prime is equal to 1 over q plus 2 times the derivative of inside, which is also 1. So here we substitute in the quotient rule. Denominator squared is ln of q plus 2 all squared. Denominator times derivative of numerator, which is 25, minus numerator times derivative of denominator, which is 1 over q plus 2. Now we make common denominator here so that we get this form for the marginal revenue. Next, we take an example. In a biology lab, we have a bacterial culture, and the activeness of this bacterial culture depends on the temperature of the surrounding. We call it capital T, and the activeness is a function of T given by A of T is equal to 12 ln of T over C minus T minus C. C is a constant. So we are asked to find the rate of change of A with respect to temperature T. So we start our solution, rewriting the A of T as follows. We have it in front of us, and then we make a common denominator. So here we have T minus C into C minus T all over C minus T. Next, we apply the property of the logarithm of quotient. So logarithm of A over B is equal to logarithm of the numerator minus logarithm of the denominator. So here we have the 12 ln. Again, I'm simplifying, and now I'm applying numerator, logarithm of numerator minus logarithm of denominator. In the following step, we will differentiate, and the derivative will be, taken term by term. So here we have dA by dt is equal to 12 into square bracket, and then we differentiate the first term. We have 1 over inside times derivative of inside. What's the derivative of inside? It is 1 plus c, and the derivative of the minus c squared is 0. For the second term, we have a minus sign here, so we differentiate and take into account that there is a minus sign here. The derivative of the ln of c minus t is 1 over c minus t multiplied by the derivative of inside, which is minus 1. Minus times minus will give us a positive sign. And that's it for this slide. We move on. And here we come to our last slide in this presentation, where we are asking you to find an equation to the line tangent to the curve y equals ln of x squared minus 3x minus 3 at x equals 4. So we start our solution. We say that x equals 4. What's the corresponding y? Y is equal to, we plug in 4 for each x, we get y is equal to ln 1, which is 0. Also, we know that the equation of a straight line needs a point and a slope. Okay, so here we have the point, which is 4 and 0. Next, we need to find the slope. Okay, so this is the 4 and the 0, our point. We need to find the slope. The slope is equal to the derivative of the function evaluated at x equals 4, and we call it m. Okay, so we differentiate this y so that we get dy by dx, and then in the derivative we put x equals to 4. Of course, we have a logarithmic function, so the derivative will be 1 over inside. We have it here, 1 over x squared minus 3x minus 3 multiplied by derivative of inside. What's the derivative of x squared? It's 2x. What's the derivative of minus 3x minus 3? It is minus 3. Now we put x equals 4. We calculate y prime as follows. So here we have 5 for the y prime, which is equal to m, the slope. We take this m with this equation of straight line here, and the point 4 and 0, we plug in the values for x1, y1, m, and we find an equation of the line tangent to the given curve at x equals to 4, which is equivalently written as y is equal to 5x minus 20.